All right, good morning, or whatever time it is for you. So, I want to talk to you a little bit about fractions and repeating decimals. And this is something that has come up when we talked about division, and specifically the connection between division and fractions. So, let's think first just a little bit about a fraction. So, if I have the fraction 2/3, then by our definition of a fraction, the numerator is telling us that we have two parts of a whole. So maybe this is 2/3 of a pizza. So I have two pieces of pizza, and those pieces of pizza are equal. And what's the size of each one of those pieces? Well, it's 1/3 of a whole pizza. So I can draw my pizza and I can partition it into thirds and just take two of those pieces. Okay, so that's 2/3 of a pizza. Now, on the other hand, we can think about a division problem. So we can think about having two pizzas. So I guess I'll just draw them. So two pizzas. And then I want to divide equally amongst three people. And so what do? I have these two pizzas, and we've seen this idea before. So one thing I can do is I can just, I can either just start partitioning up the pizzas and dividing out the pizza to the different people. But one way we can do it is we can partition each one of the pizzas into three equal parts. And now why am I partitioning the two pizzas into three equal parts? Because I have three people that I'm trying to divide the pizza amongst. That's sort of this how many groups, right? I know how many groups, there are three, but I want to really know how many units or how much pizza does each person get. Well, here's where I can just say, well, the first person's going to get one piece from this pizza and one piece from this pizza. The second person is going to get one piece from this pizza and one piece from this pizza. And then finally, the last person will get one piece from this pizza and one piece from this pizza. So each person gets 2/3 of a pizza, right? So I can draw, so one of these amounts of pizza. Okay, so that's the amount of pizza that each person gets. It's 2/3 of a pizza. But what is the difference between these two questions? This is just 2/3 of a pizza. This situation, I really have two pizza and three people. I really am doing a division problem. And now what is the division problem I'm doing? Well, I'm doing my two pizzas, and dividing by 3. And now this is this sort of really cool, miraculous fact that the answer to this division problem is in fact 2/3. And we can really understand that in the same way that we've been understanding fractions all along. 2/3 of a pizza. It's two pieces, each of size 1/3 of a whole pizza. Okay, but now a lot of times we don't really want a fraction answer. We want, well, it would be great to have a whole number answer, but maybe one better is to have a decimal answer, to really have a number sense of how big the number is. So let's think about what 2 divided by 3 is as a decimal and sort of see this phenomenon that comes up with repeating decimals. Okay, so I'm going to do something very silly. I'm going to divide 2 by 3. Okay, 2 by 3. Now, of course, 3 does not go into 2. So what do? Well, we changed the base unit. So this is just a good reminder. If you think way back, we talked a little bit about changing the base unit when it comes to decimals. So instead of thinking about this as 2 just units, I can actually think about it as being 20 tenths of a unit. So again, that's just using the structure of the base 10 system that comes built in with our numbers. It's the same thing like when we see 20, we can think about that as 2 tens or 21s. So now I want to think about this 2 as being 20 tenths. And now I can actually do this division. Because how many times does 3 go into 20? Well, 6. And now I really want to specify that I'm not putting, okay, so if we think about this as 3 equal groups and I'm putting units into those equal groups, I'm not putting whole units into these equal groups. I'm actually putting tenths. I'm putting 6 tenths of a unit. So what I can do is just put that decimal there to, again, remind myself that this is not 6 whole units, it's really 6 tenths, because I'm taking these 20 tenths and distributing them. So then what is this? Well, when I distribute these 6 tenths to the 3 equal groups, I get 1.8. And then what do? I'm left with 2 tenths. Okay? And now I can repeat the process over again. So this is 2 tenths, but now I can't put 1 whole tenth into each one of these 3 equal groups. So I need to actually now think about these 2 tenths as being really 20 hundredths. And this is where this idea comes in of bringing down the next decimal place. So, okay, now this is really 20 hundredths. And then we can do the same thing again. There are, of course, 6 hundredths that we can put in each one of the equal groups. 6 times 3 will give us 18 hundredths. And then we're left with 2 hundredths. Okay, so you see a pattern starting to form. You have 20 tenths. You can put 6, and you have 2 tenths left over. Then I can think about that as 20 hundredths. I put 6 in each group. I have 2 hundredths left over. Then I can think about that as 20 thousandths, then 20 10,000ths. And it's really cool and really interesting that the remainder here is always 2. Okay, so there's something special about this division problem. You can see that no matter how many times I do this, I'm going to always get a remainder of 2. So I'm always going to do this process where I get to distribute 6 of whatever those units are. So, of course, the way we signify this when we notice there's a pattern is we draw a bar over the part that repeats. So this is just saying, okay, well, I've done this enough. I see the pattern. This is going to repeat. And now, of course, this is 0.666666666 repeating forever because, again, I'm always going to get a 6 when I do this division. Now, here's the interesting question. Will we always get a repeating decimal? Okay, so if I take 2 whole numbers, let's say I take 157 and divide it by 63. Okay, do I get a repeating decimal? Well, what do you think? Well, maybe I would encourage you to do one more example, but you'll find that actually the answer is yes in this case. If I divide 157 by 63 in the way that I know how to, and sort of extending the decimal by changing the base unit to tenths, hundredths, thousandths, whatever, then I'm going to get a repeating decimal. And in fact, this is always going to be the case. So this is a fact that you can take to the bank. And the fact is that when dividing whole numbers, we will always get one of two things. I mean, we may not get a repeating decimal. We might actually get a terminating decimal, right? And that's sort of the case when the number goes into the other number evenly. So if I divide 15 by 3, I get 5, right? There's no repeating part to the decimal. It is just 5. So that's kind of a special case. That's called a terminating decimal. But if we don't get a terminating decimal, we will get a repeating decimal. So we will always get either a terminating decimal or a repeating decimal. So if you're a very curious individual, which I hope you are as a teacher, you should really wonder why this is true. I mean, there's really no reason on the surface to think, oh, of course, that's clearly going to be true. Why, when I divide 157 by 63, am I just going to get a repeating decimal? Well, the answer actually lies in something that we're going to touch on briefly next semester. So unfortunately, I don't really feel comfortable walking through the steps of why this is true right now. I just think that maybe there would be too much I would have to sort of say, and I would probably lose you. But hopefully in the future it's something we can talk more about. But again, I'll just tell you that the answer lies in what's called modular arithmetic. And the basic idea, you can sort of see it here in this example. The basic idea is that once I get a remainder and I have just a base 10 number of 20, well, the pattern is always going to repeat, because when I get this remainder of 2, I'm going to sort of cycle through these remainders as I divide numbers by 10 in some sense. Okay, so I know that doesn't really make a lot of sense. Again, to really answer it, I need to say a little bit more about what I mean by modular arithmetic, but the idea is sort of here, that once you kind of get a pattern, you're going to be stuck in that pattern. And that's, again, described by this idea of modular arithmetic. Okay. So while I'm not going to tell you all the details about why when you divide two whole numbers, you either get a terminating decimal or a repeating decimal, even though it's true, what I do feel comfortable telling you about is the other direction. So let's say we start with a repeating decimal. So start with a repeating decimal. And I'm going to give you a concrete example, just so we can really see what's going on. And I want it to kind of be arbitrary because I want to show you how powerful this line of reasoning is we're going to use. So let's just say 0.7145. And then all of that is repeated. So again, just to remind you what this means, this just means 0.7145 and then repeat 7145, etc. Okay, so 7145, 7145 forever. It's repeating. So if you believe me with what I just said, it's not unreasonable to think that there should be a fraction that this decimal is coming from. And that is actually also true. So there is some fraction. Again, this is another fact. there is a fraction, a over b, whose decimal representation is exactly this decimal number that I wrote down. And now I really wanted to make the point that I wrote down a very specific decimal number, but I literally could have wrote down any repeating decimal, and this fact is still true, that there is a fraction, so a ratio of two whole numbers, whose decimal representation is exactly this number. So to sort of convince you why this is true, let's actually just find the fraction whose decimal representation is 0.7145. And I think if I do that, hopefully you believe that I really did just make up these numbers, and you can start to believe that really giving any repeated decimal, you can find the fraction whose decimal representation is that number. So this is sort of the opposite question with what we started with. We started with, given a fraction, what is the decimal representation? It's always going to be either a terminating or repeating decimal. This is the opposite direction. If you have a terminating or repeating decimal, then you can work backwards and figure out what the fraction is that creates that terminating or repeating decimal. Of course, if it's a terminating fraction, that's a really easy thing to do. You just take the decimal and then divide it by whatever power of 10 gives you that terminating decimal. But for a repeating decimal, it's a little bit more complicated, but it's very interesting. Okay, so let's see how this is going to work. Okay, so remember our goal is to take this relatively arbitrary number, repeating decimal, 0.7145, and figure out what its representation is as a fraction. So I need to find the two whole numbers, a and b, for which this repeating decimal is equal to a over b. Okay, so we talked a little bit about arithmetic progressions, and I just want to give you some terminology sort of to tell you where this fits into a curriculum. So this is really going to use something called geometric progressions. So arithmetic progressions are basically just sequences of numbers where you add the same thing every time. Geometric progressions are sequences of numbers where you multiply by the same thing every time. So that's really the backbone of what we're going to be doing here. We're going to be basically adding up a geometric progression. Okay, so what are we going to do? Well, I want to actually think about what this means. So 0.7145 repeated is going to be, well, the first part of this number I can write as 7145 over 10,000. Okay, so why 10,000? I'm not saying this is the answer. This is just the first four digits, 0.7145. That terminating decimal, if I ignore the rest, I can write as 7145 over 10,000, because when I divide by 10,000, I just move the decimal point over that far. And then the next repeating sequence point, 7145, is going to start here after 4 decimal points. So I can write that as 7145 over, okay, I need to move the 7145. I need to move the decimal 4 places to get it past these 4 digits, but also 4 more places to actually place it in the right spot in the decimal representation. So this should be a 1 with 8 zeros. 2, 3, 4, 5, 6, 7, 8. Okay. So again, what is this doing? When I divide 7145 by this huge power of 10, it's just going to move the decimal point 8 places, so it's going to be 0.00007145. The first 4 zeros are where this 0.7145 fits in. Okay, so in other words, this is 0.7145 plus 0.00007145. Okay, and I can just keep doing this. And then I can do the same thing down here. So I'm really just adding up a bunch of fractions. Now I don't want to actually just add up the fractions because there's actually infinitely many, because remember, this decimal never stops. So I'm going to have to keep adding up smaller and smaller fractions to fill in all the decimal places here. So what do? I mean, I want to try to figure out exactly what the fraction is. And I don't want to just sit here and add up infinitely many fractions. That sounds terrible. So what do I want to do? Well, first of all, I'm going to cheat a little bit and write this in a little bit more compact form. So instead of actually writing out all these zeros, I'm going to use scientific notation. So this should be 7145 over 10 to what power? Well, first, second, third, fourth, just how many zeros I have. And then this is going to be 7145 over 10 to the 8th power. And then I'll have a 7145 over 10 to the 12th power. And now hopefully you can start seeing the pattern that when I'm repeating 4 digits, so I just put the 4 digits over 10 to the 4th, and 10 to the 8th, and 10 to the 12th, and 10 to the 16th, etc. And so now what I can do is all of these are being multiplied by 7,145. So I can use the distributive property and factor that out. And now I have 1 over 10 to the 4th plus 1 over 10 to the 8th plus 1 over 10 to the 12th, and so on. So what I really need to know is what is the sum of 1 over 10 to the 4th plus 1 over 10 to the 8th plus 1 over 10 to the 12th. And now this is actually the sum of a geometric progression. So what I'm doing is this first term, to get to the next term, 1 over 10 to the 8th, I'm just multiplying by 1 over 10 to the 4th every time. So 1 over 10 to the 4th, if I multiply by 1 over 10 to the 4th, I get 1 over 10 to the 8th. And then if I multiply by 1 over 10 to the 4th again, I'll get 1 over 10 to the 12th, and then if I multiply by 1 over 10 to the 4th again, I'll get 1 over 10 to the 16th. And so you see each term I'm adding up, I'm just multiplying by the same thing from the previous term. So this is the sort of thing that you can actually add up, and let's see how that works. Okay, so what I want to do now is actually add up these numbers. 1 over 10 to the 4th plus 1 over 10 to the 8th plus 1 over 10 to the 12th, etc., etc., etc. And here's the idea. I'm going to give this number a name. I'm going to call it S. for sum, because I'm adding up numbers, whatever. And now look at what happens if I take s and divide it by 10 to the fourth. What is that going to do? Well, it's the same thing as multiplying by 1 over 10 to the fourth. And we've already seen what happens to these terms in this geometric sequence when I multiply by 1 over 10 to the fourth. When I multiply 1 over 10 to the fourth by 1 over 10 to the fourth, I get 1 over 10 to the eighth. If I multiply 1 over 10 to the eighth, I'm going to get 1 over 10 to the 12th. And then 1 over 10 to the 12th, when I multiply by 1 over 10 to the fourth, I'll get 10 to the 16th, and so on. And the interesting thing is that when I've divided by 10 to the fourth, it looks very similar to what I started with, but I'm really just missing this first term, right? All the other terms are going to be there. Here they are, because I just take all of these terms and multiply by 1 over 10 to the fourth, but I'm just missing this first term. So what that tells me is that if I add 1 over 10 to the fourth to this sum, I'm going to get exactly what I started with. So all these other terms are coming from here, and I'm just adding in this missing term. So this is really just equal to s. But now look here. I actually have an algebraic equation for s. Okay, so what do I mean by that? Well, let me multiply both sides of this equation by 10 to the fourth. Then what I'm going to get, okay, so if I multiply, just actually write down what I'm doing, try to not skip too many steps. Okay, so I'm just going to multiply both sides by 10 to the fourth. So I get s, because when I multiply 10 to the fourth by s over 10 to the fourth, I get s. And then I'm going to have 1, right, because 10 to the fourth times 1 over 10 to the fourth will just be 1. And that's going to equal 10 to the fourth times s. And now I can just solve for s. This is really just an algebraic equation. So I can subtract. Okay, so maybe it's been a while since you've done some algebra, but this is like the variable x. I'm trying to solve for x. So the idea is I want to get all of my unknown terms on the same side of the equation. So I want to subtract 10 to the fourth times s. So I have s minus 10 to the fourth times s is equal to, well, let me subtract 1 to the other side. And now the idea is I can use the distributive property here. I can factor out s, and I'll have 1 minus 10 to the fourth. So again, I just factored out an s. What am I left with here? And that should equal -1. But now, if I put all this together, I've actually solved for s. So 1 minus 10 to the fourth is going to be negative 9,999, because remember 10 to the fourth is 10,000. So I'm really just taking 10 to the fourth and subtracting 1, but it's really going to be negative. So this is really just saying that negative 9,999 times s, which is this, is equal to -1. But I can just divide both sides by negative 9,999, and I actually get that s is 1 over 9,999. All right, and now we're ready to actually see what that repeating decimal is as a fraction. Okay, so recall that our original question was to find the decimal representation of 0.7145 repeat. And we had sort of broken it down to the point where we had 7,145 times this geometric sum that we actually just computed what the sum is. And so recall that this was actually equal to 1 over 9,999. But now we see what the fraction is. So what is this equal to? Well, 7,145 times 1 over 9,999 is 7,145 divided by 9,999. So this is the fraction that if I actually do the division and figure out what the decimal representation is, I'm going to get exactly 0.7145 repeating. Okay, so that's just a brief introduction to the connection between fractions and repeating decimals. So again, we saw this pattern that when I take two whole numbers and divide them, I'm going to get a repeating decimal, if not a terminating decimal. And then we actually saw an example of how we can take a repeating decimal and figure out the fraction that it comes from. Okay, so I hope to talk a little bit later about modular arithmetic, and maybe we can come back to this question. But for now, I think that's a good introduction. So I hope you enjoy your break, and I will see you probably next semester. So take care.